What's happening, y'all? Welcome back. We are continuing our conversation about the standard eigenvalue problem, in which we start with a given matrix coming from a modeling context. This is a square n by n matrix called A. And then we search for scalar vector pairs, eigenvalues lambda, and eigenvectors x, such that when I multiply A by x, I get lambda times x. In our work with the standard eigenvalue problem, we're going to get to know this matrix equation through work with an authentic real-world modeling problem that each of us does in this class. More specifically, we're going to look at a problem that I called the coupled pendulum problem. The coupled pendulum problem is analogous to a three-spring, two-mass system where the springs on either ends have been replaced with pendulum motion. Before we dive into that though, let me explain my approach here, since it is what I would call non-standard. I'm going to claim that we're going to study the standard eigenvalue problems by studying a physical, measurable problem. The reason I want to lead our study of this problem with a real-world phenomenon is that I believe that mathematics is most powerful when each of us feels that the math that we study matters in our life, is important in some way to describe the world that we live in. Thus, one of the first goals that I have in helping you explore the standard eigenvalue problem is to recognize this problem as existing in your life and helping you cultivate your curiosity and interest in describing a relatively complex phenomenon called a coupled pendula system. Not only do I recognize that your curiosity, your questions, your interest is a super important component of our study of the standard eigenvalue problem, but I recognize that many of you are not taking linear algebra as a terminal course. Another way to say that is, many of you are taking linear algebra as a prerequisite to other fields of studies and probably have a very beautiful question, which is, how can I leverage the work that I study in this class to get information that will help me in my future? With that in mind, remember back to our introductory video where we said spring mass systems were fundamental in so many of the applications across different fields. That highlights my second motivation for showing you how to translate the coupled pendula problem into the template for standard eigenvalue problems, which is to help set a foundation that you can build into your future classes to leverage this material. With these goals in mind of igniting your curiosity and interest, as well as setting you up to use this theory in your future, let's go ahead and start our study of the standard eigenvalue problem using a powerful keystone application. That application is the coupled pendula problem. Pendula is the plural of the singular pendulum. Here we see an ideal model, which we'll talk about in a second, of two separate pendulum. We have this rod connected to a ceiling. At the bottom of the rod is one mass on one of them. There's a separate rod connected to the ceiling. There's a separate mass on that second rod. Both rods have length L, which is measured using a ruler. In between the two masses, we connect a spring. So we connect the one side of the spring to the first mast, the second side of the spring to the second mast, and then literally we just move one of the pendulum and the thing swings back and forth after we've set it in motion. The coupled pendulum problem is, can we predict quite accurately the dynamics of each mass in this system over time? And another way to say predict the dynamics is figure out the location of each mass as they move at any time t during a specific observation. While I like this diagram as an idealized version of describing the problem, it allows us to refer to different components of what we're looking at, I actually don't like this visual as a way to motivate it because it's not a real world problem. We can't measure this. This is just a picture. With that in mind, we're actually going to switch over to some real world equipment that I like to call the McCusker Apparatus, a name in tribute to a co-author and mentor of mine named Michael McCusker. Before we dive into some of the features of the McCusker Apparatus, I should say that this work came from a paper that Mike McCusker and myself wrote called Make the Eigenvalues problem resonate with our students. You can find a lot more about that paper and this larger project by going to appliedlinearalgebra.com, go down to my publication list, so Jeff's publication, and then you see that first publication, Make the Eigenvalue Resonate. There is a support website with a link here, so it actually says companion website. Go ahead and click on that. On that website, you'll find the actual paper that we published, a bunch of information about the McCusker apparatus and how this works, including instructions on how to build one for yourself if you'd like, some videos about how the setup works, experimental videos, as well as experimental analysis, and a lot more information. For now, I'm going to kick it over to Mike so that he can tell you in his own words how he designed this apparatus.